Now our next discussion will be about modern representation of vector in Cartesian coordinate system. Cartesian coordinate system, as per the convention x, y, z, this is origin. So we know for any point P having coordinate x, y, z, we can write a position vector of this point OP. This is vector OP, as we have discussed by the definition of position vector. So by convention, we have three vectors I, J, K. These are three unit vectors. Vector I is defined as a vector having modular magnitude unity equal to 1, and its direction is about positive x-axis. I. Similarly for J, this is a unit vector in positive y direction. Unit vector. Similarly, K is unit vector in positive z direction. This is also a right-handed vector system, which we will discuss in cross product. What is right-handed vector system? So this is the definition of I. I is a unit vector in positive x-axis. J is unit vector in positive y direction. K is unit vector in positive z direction. So now we will represent any vector in this Cartesian coordinate system in terms of I, J, K. You can see. To solve the physical problem, you can also assume, you can give any representation to I, J, K. You can assume I as a unit force in x-axis, J as a unit force in y-axis, K as a unit force in k-axis. Similarly, I can be assumed as a unit velocity in x-axis, positive x-axis, unit velocity in y-axis, J, and K unit velocity in z-axis. So you can give any vector, you can assume this I, J, K as any in terms of any vector, but it will always represent unit vector in positive direction of x, y, z. For vector algebraic purpose, we will give some basic definitions. So let's suppose point x, y, z is coordinate. So what is the position vector of OP in terms of I, J, K? I, J, K. How will we define vector OP whose coordinate is x, y, z? So just consider this point P. This is x, this is y, this is z. Coordinates are x, y, z. This is in space. I, J, K are unit vectors. So let draw perpendicular on xy plane. By definition of this coordinate Cartesian system, this distance will be x. We have drawn a perpendicular from P to xy plane and xy plane to perpendicular on x and y axis. This axis will be this distance and this distance will be y. So there will be a vector, this. Let this is vector R. So this vector R is xi plus yj. In this direction, unit vector is I. In this direction, unit vector is j. So this vector O, let us say this point is A, let this point is B. So we can write OA, vector OA is equal to xi. Similarly, vector OB is equal to yj. Vector OA plus vector OB is equal to vector R is equal to xi plus yj. We have got this vector. OA and OB is this vector. Now draw perpendicular from P to Z. So this length is Z as per the definition of Cartesian coordinates. So this vector, let this vector was R, this vector is Q. This vector is ZK. These two vectors are perpendicular. So this OP vector, vector OP is sum of vector R and vector, let this is OL. So vector OP is sum of vector R plus vector OL. These both are perpendicular. Z axis is perpendicular to xy plane. So ZK and this R vector, these both vectors are perpendicular. And P, if you will draw parallelogram, let us draw parallelogram in two-dimensional axis. Then parallelogram will be like this. ZK xi plus yc. This will not be parallelogram. This will be a rectangle because these all vectors are perpendicular to each other, x, y, z. So this vector is this is in z direction. So OP vector is OP. This vector is R. When you will visualize it in plane OP and R, vector OP and vector R plane, then you will see vector OP, vector O, this vector R, and this perpendicular vector. These both vectors are perpendicular, ZK. So you can say OP by parallelogram theorem, OP is equal to ZK plus R is equal to ZK plus XI plus YJ, or you can say XI plus YJ plus ZK. This is the position vector of point P having coordinates x, y, z. So we have proved from addition of vectors law by using triangle law, by using parallelogram law, that in Cartesian coordinate system having I, J, K vectors, unit vector in x, y, z direction, the position vector of point P, that is OP, will be equal to x, I, y, j plus z. Similarly, now we have found the vector OP is equal to xi plus yj plus z. Now what is the magnitude of this vector? Again, from this system, let this is P, this is X, is Z, this is Y. So we have drawn a perpendicular. Coordinates are X, Y, Z. So length of OP this length OA, this OA is equal to, as per the definition, this distance, this is Y, this distance is Y, this distance is, this distance will be equal to this distance, this is X. So this is a right angle triangle. So OP will be under root x square plus y square. As per Pythagoras theorem, we have drawn a perpendicular on xy plane. This is point P. So sorry, this is A. This is A. As per the definition of x and y, if this from A, I have drawn perpendicular on x and y axis. So this x, this perpendicular intersection from O to on x axis will have x distance. Similarly on y, this perpendicular will have y distance. So this x will be equal to this. This is a right angle. You cannot you may see it as a, this will be actually a right angle. This distance is x. So this distance will be x. This distance is y. OA is under root x square plus y square, because this is a right angle triangle. Now this OA is known. Similarly, draw a perpendicular on z axis. So this distance is z. So this OP you can draw in two-dimensional. This is OA and this is OZ and this is P. So this is a right angle triangle OA and this is Z, so this will also be Z. So from Pythagoras theorem, OP square is equal to OA square plus Z square. OA square is x square plus y square plus Z is Z square. So OP is magnitude of vector OP. So magnitude of vector OP is this distance. We have calculated distance of point P from origin. That distance will be magnitude. So the magnitude will be x square plus y square plus z square. So we have seen that for a particular point having coordinate x, y, z, its distance from origin is under root x square plus y square plus z square. By Pythagoras theorem, by dividing this point from Pythagoras theorem, we found the distance OP. This distance OP is the magnitude of position vector of point P with respect to O. OP vector, which is xi, yj, zk, and magnitude of this vector is under root x square plus y square plus z square. So we have found the magnitude of position vector. Similarly, we will find a vector in Cartesian coordinate system joining two points. Let this is point P1 and this is point P2. This is x, x1, y1, z1, and this is x2, y2, z2. Coordinates are like this. So from earlier discussion, we can say OP vector is x1i plus y1j plus z1k. Similarly, this is OP1. OP2 vector is x2i plus y2j plus z2k. From the formula of position vector which we have discussed earlier, vector P1, P2, vector P1, P2, this vector is equal to OP2, vector OP2 minus OP1. This formula we have discussed P1 P2 is position vector of P2 minus position vector of P1. So OP2, this is OP2, x2I plus y2j plus z2k minus OP1 vector, OP2 vector, OP2 minus OP1 x1I plus y1j plus z1k. So here we can see we can, as these vectors are I, so we can algebraically add components of I, components of j, components of k. So these are the components of vector OP, these are the components of vector OP2. So the I component, both vectors, can be algebraically added. So it can be written as x2 minus x1 I, because these are collinear vectors, they can algebraically add it. Similarly, j y2 minus y1, these y2j and y1j, these are collinear vectors, they can be added algebraically. Similarly, z2 minus z1k. This is vector P1 P2. So we can say for a vector joining two points P1 and P2 having coordinates x1, y1, z1, x2, y2, z2 is given by equation this. This is the equation, this is the expression for to find the vectors joining two points P1 and P2 with points x1, y1, z1, x2, y2, z2. Now from coordinate geometry we know the distance between P1 and P2 is under root x1 minus x2 square plus y1 minus y2 square plus z1 minus z2 square. P1 P2. From coordinate geometry you know this formula. So you can say the modulus of this vector will be length of P1 P2, that is distance between point P1 and P2. x2 minus x1 square, x2 minus y1 square, z2 minus z1 square. So this is formula for finding modulus of this vector P1 P2. So we have discussed how to represent a vector in Cartesian coordinate system, how to represent a position vector of point, how to find its magnitude, how to represent a vector joining two points, and how to find the magnitude of this vector joining two points in terms of I, j, k. Similarly, if you see any vector A in Cartesian coordinate system, let it is represented xi, yj plus zk. So this vector can, as we have discussed, vectors are free. So this vector, let this is a vector in Cartesian coordinate system, x2 minus x1 xi plus yj plus zk. After applying the formula of x2 minus x1, y2 minus y1, z2 minus z1 for two points P1 and P2, we find this vector xi, yj, zk. So you should not think that this vector will stick at this place only, because vectors are free. So there infinite number of combinations of points, which combination will represent the same vector. We can have same vector P3, P4. This vector will also be xi plus yj plus zk. You can imagine these P1 and P2, these were 2 points x1, y1, z1, x2, y2, z2. We found the vector P1, P2 by x2 minus x1 I, y2 minus y1 j, z2 minus z1 k, and this came to this. Similarly, same vector, same value can be found for infinite number of combinations of points P3 and P4. So there can be 2 other points whose x2 minus x1, y2 minus y1 will be same. So there can be n number of vectors having same expression. There are infinite number of combination of points, pairs of points like this. There are another pair of points. This vector will also represent same by finding P5, P6. When you find P5 vector P5, P6 by x2 minus x1, x3, so you will get the same. So there are possibility of infinite number of pairs of points in this space which will represent same vector, and there will be a single point also for which position vector will be equal to this vector. A single pair point will also exist. Suppose we found x, y, z. For example, let there are 2 points 3, 4, 5. P1, P2 is 6, 7, 8. For example, so vector P1, P2 is equal to 6 minus 3, 3i, 7 minus 4, 3i, 3j, let it is 6, so it will be 2, plus 8 minus 5, 3k. So this is a vector joining these 2 points. There can be another combination of points which will give same vector. For example, this is 4, 5, 6, another point, and this is 7, 7, 9. So vector joining these 2 points will also be 3i plus 2j plus 3k. Similarly, you can have another combination pair of points. So you have infinite number of pair of points giving same vector. So our statement of free vector applies here also, because there are infinite number of pair of points which will give same vector. This vector you can achieve by P1, P2, P3, P4, P5, P6, infinite number of pairs you can construct to find this same vector. So once you find a vector P1, P2, you don't think this vector is sticked at this place only, P1, P2. Once you have found it, P1, P2, by calculation, then this is a free vector. It can be represented anywhere between suitable pair of points by selecting suitable pair of points anywhere in space. Infinite number of representation, infinite number of pairs will be there which will represent same vector, and there will be a point P which is 3, 2, 3. This point will have position vector equal to 3i plus 2j plus 3k. A position vector will be unique. Point P will be unique, 3, 2, 3. So you can see, once you find the vector in terms of ijk, this is a free vector and it can be represented by any suitable pair of points selecting at different location, different space, different. So the concept of free vectors I wanted to explain here also, because you should not think there's only these 2 points this vector is possible. This vector is possible by infinite number of pairs of points. But this vector is specific for only one point whose position vector is this. Position vector for this point only, it will be position vector. Otherwise, there will be infinite number of pairs of points which can give the same vector. So I, J, K, you don't think this I is strict from origin to here in this direction, in this is location only. J on at this and K at this. I can be here also. I can be here also. So for example, there is one point P1 and P2. This coordinate is 1, 2, 3, and its coordinate is 2, 2, 3. So you can say P1, P2 is equal to 2 minus 1 I plus 2 minus 2 J plus 3 minus 3 K, which is I. So you should not think that I is only in x-axis, located only at x-axis starting from 0 to unit distance. I, this vector P1, P2 is also I. Similarly, there is a point P3, this is 1, 2, 3, and this is P4, which is 1, 3, 4, 1, 3, 3. So P3, P4, vector P3, P4 is 1 minus 1I plus 3 minus 2 J plus 3 minus 3 K, which is equal to J. So this vector is J. Here I have written horizontal, but actually it will be vertical. I have just explained you to explain you assume this. Otherwise P3, P4 will be in vertical direction, in the direction of J. This is I, this is J. So P3, P4 is J. This is not sticked at y-axis. So you can have, I want to explain that I, J, K are not strict on the axis only. It can be anywhere. By vector I can be here also. Vector I is here also. This vector is also I. This vector is J. So similarly for K, it can be in space anywhere vector I, anywhere vector J, anywhere vector K. But its direction will be as per the definition. I will always be anywhere. It can be here also, in negative axis also, anywhere, but its direction will be along positive axis and magnitude will be unity. Similarly, J can be here also. This can be J also. Its direction will be positive, J direction, and magnitude will be unity. So here I want to stress the vectors are free. They are never tied at a particular location, particular position. For operation, you can assume vector I, as we have explained here, P1, P2, this vector is I. P3, P4, this vector is J. P3, P4 point are here, but vector is J. It is not like that vector J is along the on the x-axis only, y-axis only, starting from 0 to unit place, or I-axis starting from 0 to unit place on the x-axis. Don't think like that. So any vector is free and it can be anywhere. That we want to discuss. I want to communicate with you. So vectors are always free. Just keep in mind. Now another important thing about vectors is cosines of vector, which gives about idea about direction of vector. So we will briefly understand what is cosines of vectors. So for x and y axis, just take only for x and y axis for example, because it is simple to represent in. Let there is a point x and y, point P. This is O. This is vector OP, and this is angle from x axis is alpha. Angle from y axis is beta. So this vector, we know cos alpha is equal to, as per the definition, this distance will be x. Cos alpha is equal to x by OP. Mod of OP is equal to x by under root x square plus y square plus z square. Similarly, cos beta will be, you see this perpendicular, this distance is y. Y divided by mod of OP is equal to y by under root x square plus y square. So these are called the cosines. Here you can see what is x divided by under root x square is, this OP is xi plus yj. So unit vector in OP direction will be OP by mod of, and this will be x divided by under root x square plus y square I plus y divided by under root x square plus y square j. This is unit vector in OP direction. That is vector OP divided by its mod. Mod of OP is under root x square plus y square by Pythagoras theorem, under root x square plus y square distance OP. So x, so this vector will be OP x divided by under root x square plus y divided by under root y square. OP divided by, put the value of OP is. So this x divided by under root x square is cos alpha. You can write it like this, cos alpha into I. Similarly, y divided by under root y square is cos beta plus cos beta j. So this is unit vector in OP direction. So we can say for any vector, now we can generalize this statement for 3 dimension also, as we have proved it for 2 dimensions. You can also easily prove it for 3 dimension also, x, y, z, I, j, k in this direction. So for a point P, x, y, z, OP is equal to xi plus yj plus zk, that we have proved. OP vector. Mod of OP is equal to under root x square plus y square plus z square. That is distance of point P from O, which is under root x square plus y square plus z square. Similarly, cosines of vector OP are, suppose this makes angle alpha with x-axis, beta with y-axis, and gamma with z-axis. So as we have derived values of cos alpha, cos beta in xy coordinate earlier, you can find value of cos alpha for 3 dimensional is x divided by under root x square y square plus z square. Similarly, cos beta, so y is equal to under root x square plus y square plus z square. Cos gamma is equal to z is equal to under root x square plus y square plus z square. These are called directional cosines of vector OP, making angle alpha with x-axis, beta with y-axis, gamma with z-axis. This vector OP makes angle alpha with x-axis, OP makes angle beta with y-axis and gamma with z-axis. Cosines of these alpha, beta, gamma is given by these expressions. So similarly, you can find unit vector OP, unit vector having modulus unity and direction similar to OP will be vector OP divided by mod of OP. So you can write vector OP is this x, y, j, z, k, and mod of OP is under root x square plus y square plus z. So you will get unit vector OP is equal to x divided by under root x square y square plus z square I plus y divided by under root x square plus y square plus z square j plus z divided by under root x square plus y square plus z square into k. Unit vector OP in direction of OP is given by this expression. From definition of cosines, you can see this is cos alpha, this is cos beta, this is cos gamma. So you can write vector, unit vector OP as cos alpha into I plus cos beta j plus cos gamma k. So this is a principle, you can remember it as a principle that unit vector in a direction of given vector is given by, in terms of cosines of that vector, can be represented in this form. So any vector R can be represented in terms of its unit vector and its cosines. So now we can say that there is a vector R. Now reverse process. R is equal to mod of R into unit vector. Now mod of R into unit vector is, in the direction of R is cos alpha I plus cos beta j plus cos gamma k. So inversely we can say any vector can be represented in terms of its cosines and its modulus. And this is unit vector, as we have said, this is unit vector in the direction of R. So for any vector, the unit vector in that direction can be found in terms of its cosines and ijk only. So R dash is equal to cos alpha I plus cos beta j plus cos gamma k, where R is unit vector in a direction of R, direction of vector R, and these cos alpha, cos beta, cos gamma are cosines, directional cosines of that vector R. So you can, this is a definition of directional cosines for a vector, and a unit vector can always be represented in terms of its cosine. A unit vector can always be represented in terms of its directional cosines, and any real vector having definite magnitude can be represented in terms of unit vector. Mod of vector multiplied by unit vector. Mod of vector multiplied by unit vector. Unit vector is cos alpha I, cos beta gamma, cos gamma k. Now another important property of directional cosines, I will just briefly write here. Cos square alpha plus cos square beta plus cos square gamma is equal to, from the formula you can see, x square divided by x square plus y square plus z square plus y square divided by x square plus y square plus z. These are the formula of directional cosine. Z square divided by x square plus y square plus z square. Just recall the formula of cos alpha, cos beta, cos gamma. Cos alpha was x divided by under root x square plus y square z square. So cos square alpha is this. Cos beta is y by under root x square plus y square plus z square. Cos beta is this. Similarly cos gamma. So this, if we will add, it will come to 1. So you can say cos square alpha, cos square beta, cos square gamma is 1. Similarly, you can replace cos square alpha is equal to 1 minus sin square alpha. So you can write 1 minus sin square alpha plus 1 minus sin square beta plus 1 minus sin square gamma is equal to 1. So you can say sin square alpha plus sin square beta plus sin square gamma is equal to 3 minus 1 is equal to 2. So these are two expressions. Cos square alpha, cos square beta, cos square gamma is 1, and sin square alpha, sin square beta, sin square gamma is 2. So these are the properties of directional cosines of a given vector, where alpha, beta, gamma are angles of that vector from x-axis, y-axis and z-axis. For any vector, here we have discussed about a position vector, but we know vectors are free. They can be arranged from here to there, anywhere. So for any vector in space between point P1 and P2, that vector will have directional cosine. So let us just complete this. So let two points are there, P1 and P2. Vector P1, P2 is equal to xi plus yj plus zk. So directional cosines, this x will be x2 minus x1, y will be y2 minus y1, and z will be z2 minus z1. x1, y1, z1, x2, y2, z2. So these are their expressions. So let x minus x1 is x2 minus x1 is this, y is this, z is this. So cos alpha will be calculated similarly as we have calculated for position vector. Cos alpha of vector P1, P2 is x by under root x square plus y square plus z square. Cos beta for vector P1, P2. This vector P1, P2 can be transferred. Let this is vector P1, P2. So it will make angles with x-axis, y-axis, z-axis, alpha, beta, gamma. So the same analogy you can use with point P1 and P2, which we have used for position vector of OP, to define their cosines. There is exact same formula. Cos beta is y divided by under root x square plus y square. Similarly cos gamma. So any point P1, P2, vector P1, P2, its cosines will be defined with same formula. It is not exclusively for position vector. It is for any vector in space, because there is no vector tied at a place. For a position vector, you can find different number of pairs representing the same vector. So the formula of cosine, directional cosine, is general. It is not only for position vector only. So let us take a small example to represent how do we represent any given vector. So let this is x-axis, this is y-axis, this is z-axis, and this is origin. So let there is point P1 and let there is another point P2. Just assume coordinate of P1 is 2, 3, 4, and coordinates of P2 is 5, 6, 7. This is just for example to illustrate how we find position vector, how we find real vector based on position vector in terms of IJK. So first of all, vector OP1, position vector of point P1 is OP1, and this vector will be 2, 3, 4. These are the coordinates. So earlier we have discussed for x, y, z general point, the position vector is xi, yj and zk. So for this point, vector OP will be represented as 2i plus 3j plus 4k. Second, vector OP2, position vector of point P2 is represented with this arrow, and this vector will be represented in terms of ijk as 5i plus 6j plus 7k. Now third vector P1 P2 will be vector P1 P2 will be position vector of P2 minus position vector of P1. So this will be OP2, that is 5i plus 6j plus 7k minus 2, 3, 4, 2i plus 3j plus 4k. So here we know that I, and there is another term I, component I. So we can algebraically add I, J, K. But for I and J, J and K, K and I, this addition is not possible because they are perpendicular vectors. So therefore resultant you have to find based on Pythagoras theorem, under root x square plus y square. But here we can algebraically find the vector is 5i minus 2i is 3i, 6j minus 3j is 3j, 4k, 7k minus 4k is plus 3j. So vector P1 P2 is given by this vector. So vector P1 P2 is 3i plus 3j plus 3k. So again I will remind you, even though this vector seems here, P1 P2 seems here, but it can be anywhere in this Cartesian space, Cartesian coordinate system. It can be here also, because you can easily find the combinations of point for which the resultant vector will be 3i, 3j, 3k. So such combinations of point will be infinite. Infinite combinations of point representing the vector P1 P2. All these vectors are equal to vector P1 P2, and similarly their combination of points can be derived. That's not very difficult. So this vector is represented in fixed vector I, J, K. So no matter what is the location of this vector, this can be assumed here, this can be assumed here, this can be assumed anywhere. But in all cases, you will find vector 3i, 3j, 3. Representation will be same. Now again, another thing we talked about, modulus. So modulus of vector OP, OP1 is, this is the vector OP1, then modulus will be under root x square plus y square plus z square. 2 square plus 3 square plus 4 square is equal to 4 plus 9 plus 16 is equal to under root 29. That is vector OP1 modulus. Similarly, vector OP2, modulus of vector OP2 is under root 5, 6, 7 x square plus y square plus z square, that is 25 plus 36 plus 7 square is 49. So this is equal to 110. So this way you can find modulus of any vector. Now similarly we will find modulus of P1, P2, this vector, which is 3i, 3j, 3k. Modulus of P1, P2 is under root 3 square plus 3 square plus 3 square, that is 9 plus 9 plus 9 under root 27. That is modulus of P1, P2 is under root 27. Modulus of OP vector OP1 is under root 29. Modulus of OP2 is under root 110. So any vector given in terms of AI plus BJ plus CK, any vector, let this is vector A, the modulus of vector A is given as under root A square plus B square plus C square. So this we have discussed earlier also. So that is the formula when a given vector is represented in terms of I, J, K. You can simply find coefficients of I, J, K and then find modulus of that vector by under root A square plus B square plus C square. This is for any given vector. Another thing we have discussed is direction of vector. So we have three vectors, OP1, OP2 and P1, P2. So we will just find by direction of P1, P2. P1, P2 is this vector. So we have discussed directional cosines, cos alpha, cos beta, cos gamma. Direction cosines are alpha is angle between vector and x-axis. So just put this vector here. This vector we have shifted here. Angle between this vector and x-axis is alpha. Angle between this vector and y-axis is beta. And angle between this vector and z-axis is gamma. So by finding alpha, beta, gamma, we can find direction of this vector. So cos alpha is equal to, for a given vector AI plus BJ plus CK, cos alpha is A divided by under root A square plus B square plus C square. We have derived this formula based on by Pythagoras theorem, simple. Another method we will use to derive this formula by dot product, which we will discuss right now. So cos alpha is A for vector P1, P2. A is coefficient of I. Coefficient of I is 3 under root A square plus B square plus C square, that is 27. 3 square plus 3 square plus 3 square. So this is direct. So from this formula we can find alpha. Similarly, cos beta is given by b divided by under root a square plus b square plus c square. b is also 3 and under root a square plus b square plus c square is 27. So cos alpha, cos beta, cos gamma, all you will find. Cos gamma also it will come 3 by under root 27. So for a given vector, you can find directional cosines from this formula. Next thing, this is one method to find the direction of given vector, but it is very few. This is not used generally, because in general questions what we will do, we study motion in 2 dimensions. At this level we study motion only in 2 dimensions. So let the point P1 in, this is x axis and this is y axis. So the point is 4,8. So this is O, that this is a vector OP. So in general questions we find direction of OP, that is alpha, by formula tan alpha is equal to, for a given vector, AI plus BJ. We have omitted K because we are talking about 2-dimensional vectors, only I and J. So for this vector, tan alpha is B by A. That you can easily find it. This point is A comma B and this is a vector. So this distance will be B and this distance will be A, and this angle is alpha. This is x-axis and this is y-axis. So from this triangle you can find tan alpha is equal to B by A. So this formula is generally used to find the direction of vector in 2-dimensional problems. So in this case tan alpha is, in this case vector OP is 4i plus 8j. As we have discussed, based on for general point xyz, vector is xi, yj, zk. So this point is 8, 4, 8 and let you say 0. Z axis, for z we have taken 0 to understand it in 2-dimensional plane. So 4i, 8j and you can say 0k. So this vector is can be omitted. So vector OP is only 4i and 8j and tan alpha will be B by A. So here B is coefficient of j and A is coefficient of I. So B by A is 8 by 4, that is 2. So alpha is equal to tan inverse 2. So for a given point AB, here the vector will be AI plus BJ. So this we have just illustrated how those formula which you have seen only formula. So we have used those formula to find position vectors, real position vector, actual vector P1, P2 by formula of position vector, and then we found their modulus and we found their direction. It can be found from cos alpha also. Cos alpha you can find it, but we seldomly use this method. Cos alpha this 4 by under root 16 plus 64. That is modulus. The formula which we have discussed, cos alpha is equal to mod of vector OP divided by, coefficient of I, that is A, divided by under root A square plus B square plus C square. So here A is 4 and under root A square, that is 4 square is 16 plus 8 square 64. So this will be 4 divided by under root 80. This can also be used to find the direction, but generally we use tan alpha simple formula, because here you have to use under root. This will make expression more complicated. Under root, that is that will come in formula of cos alpha, whereas tan alpha you can directly find coefficient of j and I. So by formula of tan alpha, formula is simple, that is b by a. So this tan alpha is frequently used to find the direction of a given vector from x-axis, y-axis. You can easily use that formula. So now we have discussed how a vector is represented in Cartesian coordinate system.